Okay, folks, our goals for today is that you can calculate the theoretical net force on the car from experiment 1 of the Newton's second law lab. So some of you might be saying, well, hey, didn't we already do that? We did already do that. We calculated the net force. In today's lab, though, we're going to be calculating the theoretical net force. So what should the net force have been on this pulley system based off of Newton's second law and our equations for net force. Earlier, we determined the experimental value. So we just took the data on the mass, we took the data on the acceleration, we found the slope between them to find the net force. Now we're gonna use our net force equations to calculate what should the net force have been. And then once we calculate that theoretical net force, we're going to calculate the percent error of our experimentally determined value by comparing it to the theoretically determined value. All right, so our agenda for today. We're going to take notes on calculating the net force in pulley systems. We're going to calculate the theoretical net force for each trial of experiment 1. And then we're going to determine the percent error between the theoretical net force and the experimental net force. Okay, so on this page, what you're going to do is just copy over your drawing of the experimental apparatus. If you want to, just go to the data collection assignment and copy and paste what you had over. It should look kind of like this. So we've got our motion detector right here. We've got the car moving. And then the car is connected to a string. The string moves over a pulley. And then the pulley is connected to a hanger mass. Now, if yours doesn't look exactly like this, that's okay. This is just my interpretation of it. But the important things that you need to have on there are the sensor, the car, the string, the pulley, and the hanger. Those are the most important features. Okay. And so then we're going to draw a force diagram on the car. So that's the other thing that I want you to do is draw your force diagrams in on here. Now, the car is being pulled, in my drawing it's to the left, and yours it might be to the right if you drew it actually like it was in the experiment. For mine I drew it so that it's being pulled to the left, and it's being pulled by the tension in the string. Other forces acting on the car, well, we've got the normal force and gravity. Those aren't really going to come into play when we calculate the net force because the car isn't accelerating up or down. It's accelerating to the left in my drawing. It might be to the right in yours, but that's okay. The only other forces that should be significant would be like drag or friction going backwards. We're going to ignore those when we calculate the theoretical net force. So if you had drag or friction going that way, that's fine. You can leave them on your diagram. We're not going to calculate them when we calculate the net force, though. But keep in mind that there probably is some drag or friction on the car as it moves to the left. Okay, and so then we're also going to draw a net force diagram on the hanger. And so we know that we've got gravity pulling down on the hanger. And we know that we have tension pulling back on the hanger. And that's from the string. And again, maybe you included some drag with your tension. I'm just going to use tension for mine. Okay, so when calculating the net force on our pulley system, you need to consider that the forces are acting in two different dimensions. So what do I mean by that? So for example, if we look at the car, the only real significant force on the car is the tension, because the normal force and gravity cancel each other out, and the tension is acting in the x direction, right? So it's pulling it to the left in my drawing. Maybe it's to the right in yours, but the tension on the car is acting in the x direction, to the left. Maybe in yours it's to the right. If yours is to the right, you can write to the right here. And so then if we look at the hanger, we can see that the forces are going to be acting in the y direction, right? The tension's pulling up, the gravity's pulling down. So the tension and the gravity on the hanger are acting in the y direction, upwards and downwards. Okay, however, the net force in the x direction must be equal to the net force in the y direction because the string keeps the car and hanger. So we can see that the string here is going to make sure that at all times the car and the hanger are the same distance apart. Right? So the net force in the x and y direction needs to be the same. We know this is true, because the car accelerates forward at the same rate the hanger accelerates downward. And again, that's because the string keeps them the same distance apart. So if that string wasn't keeping them the exact same distance apart the whole time, they might not be accelerating at the same rate. But because of that string, that's sort of connecting them all as one big system. Okay, so let's write down some equations that we're going to need to calculate net force. So this is, remember, this symbol means sigma, it means sum. So we're going to take the sum of all the forces in the x direction. So in the x direction, the only force that should be acting is tension, right? And that's pulling the car, in my picture, to the left. So our net force in the x direction is tension. Then we'll do our sum of forces in the y direction. We don't need to worry about this normal force and gravity because the car is not accelerating upwards or downwards. We do need to worry about the gravity and tension on the hanger. And so what we're going to see is that our net force in the y direction is going to be the force of gravity minus tension. We're subtracting tension because that's in the opposite direction of gravity. Okay? And so then we're going to, in our next step, what we're going to be doing is setting the net force in the x direction equal to the net force in the y direction. And again, that comes as a result of the fact that we know that the two objects, the hanger and the car, they're both accelerating at the same rate. We know that they're accelerating at the same rate because the string keeps them the same distance apart the entire time. So really, our net force in the x direction is going to equal our net force in the y direction, and this is going to just be mass times acceleration, or our net force on the system. Okay? So, because that's true, we can set our tension, right, that's our sum of forces in the x direction, equal to the force of gravity minus the tension. That's our sum of forces in the y direction. Right? These both equal mass times acceleration. These both equal the net force, so they must be equal to each other. So I'm just taking this value, the tension, setting it equal to the force of gravity minus the tension. And then we also just need to remember that force of gravity can be calculated from mass times gravity. I just want to real quick here, when we're calculating the force of gravity, it's going to be the force of gravity on the hanger, because the hanger is what's being affected by gravity. We don't have to worry about the gravity on the car because that's canceled out by the normal force. Okay, so put your experiment 1 data table from the data collection assignment here. So you can click on this if you want to go back to the data collection assignment, but basically this is just the assignment where we collected data on day 1 of this lab. So you're putting in the exact same data here. So this is kind of what I got for trial 1. Hopefully you got the same numbers. If not, you might want to go back and check your work. Okay, and so then what we're going to do is calculate the net force on the car in trial 1. So let's just go through this for example. We're using this same equation from our net force equations page. And then the first thing we're going to do is we're going to calculate the force of gravity. So that's just the mass times gravity. Well, the mass that we're looking at is just the mass of the hanger. We don't really care about the mass of the car, and we don't really care about the total mass of the system for this calculation. The only thing that's being affected, that's accelerating because of gravity in this lab is the hanger. So that's the force of gravity that we're going to calculate. 0.050, and then we multiply that times 9.8, because remember, that's the value of G. That will never change. Well, it will change if you go to another planet, but all of our calculations are going to be on Earth for this course. So it'll always be 9.8. So our force of gravity is 0.49 newtons. So we're going to put that in for the force of gravity. Okay, and then we're going to solve for T. First, we need to add T to both sides. So we're going to get 2T equals 0.49 newtons. Then we're going to divide both sides by 2. T is going to equal 0.245 newtons. Okay, so now you're going to do the exact same thing, and that's our net force, right? Because we know that our net force in the x direction is equal to T. Our net force in the x direction is equal to our net force in the y direction. So we kind of just solved for a whole bunch of stuff right now. We figured out what the net force in the x direction is. We figured out what the net force in the y direction is. We figured out what the net force on our system is for this problem. We figured out how much tension was in the string, right? Solved for all of that. All of that is going to be equal to 0.245 newtons. Okay, and so then what you're going to do in the next few trials is practice calculating the net force for each trial. And so you're going to go through and do that, and then you're going to answer these questions at the end. After you calculate the theoretical net force, you're going to compare that to your experimental value. So if you click on this link right here, that'll take you to when you linearize the acceleration versus mass. Remember that your slope from there was your experimental value of the net force. And then I've got one more little question for you to answer at the end. So give that a try. If you have any questions, let me know.